Hello, math friends. This is Pre-Calculus Section 3.1 Notes. Today we're going to be talking about polynomial functions. First, a little bit of vocabulary about polynomials. We have an example here of polynomial p of x. Notice that mine looks a little bit different than yours, so I crossed something out that I had that you didn't have. When we look at this polynomial, the first thing I want you to notice is that the terms of this polynomial are in descending order, meaning the term with the highest exponent comes first, and then they go down in descending order, and then if there is a constant term, which there is 13, that goes at the end or last. The degree of the polynomial then is the degree of the first term, because that is always the greatest exponent when it is written in descending order. So the degree of this polynomial is going to be 6. The leading coefficient is the number in front of the first term in descending order. So the leading coefficient is 7, and then our constant term is positive 13. Okay, so the reason that we care about the degree and the leading coefficient is that this affects the end behavior of our polynomial. You should hopefully remember this from Algebra 2. End behavior of a polynomial is the description of what happens to the polynomial as x becomes large. And we say large, we mean as it goes to positive infinity, or as x becomes small. And when we say small, we mean x is approaching negative infinity. Okay, so the thing that determines the shape of your graph is whether you have an even degree or an odd degree. So our odd degree polynomials are going to be our snake shapes. And if you look at the graphs, you can kind of see that. They look, a little squiggly. They got that little wiggle jiggle in the middle. One end is up and one end is down. So I refer to those as snakes. If your leading coefficient is positive, then I refer to this as a positive snake. Okay, if your leading coefficient is negative, I refer to this as a negative snake. So let's talk about what's going on. If we look at our coordinate plane, okay, our x values obviously go left to right. So when we're looking at the graph here, we're thinking about our x values either getting really big, which means heading towards positive infinity on this side, or getting really small, which means heading towards negative infinity on the left-hand side. Well, if we look at the graph, if we look at negative infinity here on the left-hand side, as our x values are getting smaller, 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 our graph is plunging down. So we would say that our y values approach negative infinity as, or the values of our function, I should say, approach negative infinity as x approaches negative infinity. So they match, right? And then on the other side of our graph, as our x values get bigger and bigger and bigger, so as our x values approach positive infinity, our graph is going up. So the values of our function are also going up. So once again, it matches with a positive snake. As x gets small, so does our graph. And then as x gets big, so does our graph. Now a negative snake, the behavior is exactly the opposite of what's going on along the x-axis. So on this one, if we look at what happens as our x values get really, really small, our graph is shooting up. So our y values are going to get large. And then on the other side of the graph, as our x values are getting large, our y values are going down, so our y values are getting small or approaching negative infinity. So those are our two snakes. Now, if our polynomial has an even degree, meaning the exponent is an even number, these are going to be, I call them parabola shapes. Now, I recognize that they don't really look like parabolas. They usually have a little bit of a wiggle jiggle in the middle depending on what the power of your polynomial is. But when I'm talking about parabolas, I'm really just talking about the two ends. What are the two ends doing? And for even degree polynomials, they're either both up or they're both down. Okay, so if we have an even degree, and again, if our leading coefficient is positive, I call this a positive parabola. And if our leading coefficient is negative, but we have an even degree, this is going to be a negative parabola. So what's going on with our graph as our values of x either get really big or really small? Well, if we look at the negative side of the x-axis first, so as our x values are getting really, really small, oh, sorry, I should be starting here with the positive parabola. I apologize. As our x values are getting really, really small, so as our x values are approaching negative infinity here on the left, our graph is going up. So our y values are getting bigger. And then on the right side of the graph, as our x values are getting really big, approaching positive infinity, our graph is going up. So our positive parabola, it's always either both up, well, I should say our positive parabola is always the function is going up on both ends, whether x is getting big or small, our graph is going up on both sides. With the negative parabola, we can see that the graph is going to be going down on both sides. So on the left-hand side, as our x values are getting really small, the graph plunges down. So it shoots towards negative infinity. And then on the right-hand side, as our x values are approaching positive infinity, our graph again is going down. So negative parabola, both approaching negative infinity, positive parabola, both approaching positive infinity. The next thing we're going to talk about is real zeros of a polynomial. We have this example, p of x. Use p of x equals x squared minus 4 to find the following. Number one, the real zeros. Well, that's easy, okay? Hopefully you recognize when you look at p of x that x squared minus 4 is a difference of squares, so that's a factorable polynomial. So right here we can say, well, p of x factors into x plus 2 and x minus 2, which gives us our real zeros, right? That tells us that our real zeros are going to be x equals negative 2 and x equals positive 2. Okay, the real zeros of a function are also called the solutions, because they are the values that make the function equal to 0, right? Or they are the x-intercepts. So now we have another example. This function is given to us in factored form. We've got this nice box here on the right-hand side that says good info to know for graphing. The basic shape of the graph, the end behavior of the graph, the zeros of the graph, and the behavior between and near the zeros. So we're going to explore this function a little bit before we attempt to graph it. The first thing is, since it's written in factored form, it's really easy for us to see our zeros, right? We can tell that this one right here is going to give us a 0 of negative 2, this one is going to give us a 0 of positive 1, and this one is going to give us a 0 of positive 3. So we have x equals negative 2, positive 1, and positive 3. So if we wanted to, right now, we could plot those points right on our graph because those are our x-intercepts. Please note here that the graph has a scale of 1 on the x-axis and it has a scale of 5 on the y-axis, okay? So let's see here, negative 2, positive 1, and positive 3. Okay. So the next thing then is I want to think about the end behavior of this graph. It's in factored form, but if I were to multiply it all together, my first term, so if I multiply the first term times the first term times the first term, x times x times x is going to give me 1x cubed. So that would be my leading term of my polynomial if I were to multiply it out. So that tells me that my degree is 3 and that the basic shape, since my leading coefficient is positive, if my degree is 3, it's going to be a snake. My leading coefficient is positive, so my basic shape is going to be a positive snake, which I know looks something like that. Okay, so that's what the shape of my graph is going to be. So I would expect on the left-hand side it's going to go down, on the right-hand side it's going to go up. So now what's left is I need to figure out what is going on with my graph between and near my zeros. That's what my table is for. So I'm going to choose some x values that are surrounding my zeros. So if I've got a 0 at -2, I'm going to plug in -3 for an x value. The values between the 0 of -2 and +1 would be -1 and 0. So I'm going to do both of those. And then an x value between 1 and 3 would be 2. And an x value bigger than 3 would be 4. Okay, so I'm hitting all of my areas on the left-hand side, between, and then on the right-hand side of all of my zeros. So I'll have an accurate picture of what's going on. To figure out the value of the function at these x values, I just have to plug these x values in. So it's going to be, my y value is going to be equal to -3 plus 2 times -3 minus 1 times -3 minus 3. Okay, you do the math on that, and you get -24. So when x is -3, the value of my function is -24. Remember, on the y-axis, I am counting by 5, so that's going to be right there. Okay. And then I'm going to go ahead and I'm going to continue with my table here. So when x is -1, my y value is going to be -1 plus 2 times -1 minus 1 times -1 minus 3. I do the math. That one's going to give me 8. So at -1, I'm at 8, which is about right there. When x is 0, that one's pretty easy. 0 plus 2 times 0 minus 1 times 0 minus 3 is basically just 2 times -1 times -3, which gives me a value of 6, which is right there. Then when I have an x value of 2, I've got 2 plus 2 times 2 minus 1 times 2 minus 3, which gives me a y value of -4. So +2, -4, it's about right there. And then finally when when x is 4, y will be 4 plus 2 times 4 minus 1 times 4 minus 3. We do the math there and we get 18. So 5, 10, 15. 18 is about right there. So now I can go ahead and connect my points. And I do indeed have that positive snake shape that I predicted. In the next example, we're going to talk about multiplicity of zeros and what that means. So we again have a function that's given to us in factored form, but notice some of our factors are repeating, okay? So our first factor has a degree of 2, our second factor has a degree of 3, and our third factor has a degree of 1. So really, we have 1, 2, 3, 4, 5, 6 factors, which means that our function has a degree of 6, okay? So this means that this function has 6 zeros. However, we don't have 6 unique zeros because some of them are repeated. Okay, our 3 zeros that we're going to get are going to be x equals 3. That comes from the first factor. That has a multiplicity of 2 because it's a 0 twice. Our second 0 is going to be x equals -5. That is the solution of the second factor. That has a multiplicity of 3 because the factor repeats 3 times. And then our third 0 is going to be at x equals 9, and that has a multiplicity of 1. And I want to add a little note here that even and odd multiplicities affect the shape of the graph. Okay, and we will talk about how they affect the shape of the graph in the next slide here.